Alright, so this is a chemistry problem, but it utilizes the properties of exponential functions. What? Math and chemistry in the same question? Impossible. Alright, a radioactive sample of radium-225. You guys know what that means? I hope. Ra-225 tells you the atomic mass of, not the atomic mass, is the atomic mass? Yeah, it tells you the atomic mass of that isotope.
Oh, right.
It's radioactive because it's got too many neutrons, so it's like an overweight atom that just loses neutrons to become slim. Wouldn't that be nice if you could just exist and have fat decay away from you?
And then after 50 years, you'd like lose.
After 50 years, you'd be like half your weight.
Arm and a leg missing.
That'd be nice. No. Okay? It has a half-life of 15 days. So that's pretty quick, right? Over 15 days, it'll be half of what it is today. Man. The mass, m in grams of radium-225, remaining over time in 15-day intervals can be modeled using the exponential graph shown. Okay? So what is the initial mass of the sample? What is it when we start calculating its mass? 1 what? 1 gram? Good. Okay. So we have 1. Should we do significant digits? They want that? Yeah, that's math. 1 gram. Don't be lazy. What value does the mass of radium-225 remaining approach as time passes? So if I did this experiment where I observed that isotope for an infinite number of days, what value would the mass approach over a long period of time? 0, right? It would never completely disappear, but it would get smaller and smaller and smaller and smaller and smaller and lighter and lighter and lighter and lighter. Okay? So it approaches 0 as time grows. Okay, that would kind of be like the horizontal asymptote, right? Okay. B, what's the domain and range of this function in this context? What's the domain?
Everything above 0. No,
Everything.
0 and above.
Yeah, I start at time 0, and then I just keep calculating time past that. Right? They don't tell me when to stop my experiment, so everything greater than 0 and equal to 0 as well. Okay, and time is a real number in this case. Range. Careful here. They want to use m for the variable. What are the restrictions on m? Good job. Okay. Less than or equal to 1, because it starts at 1, right? So the range has a maximum value of 1. It starts at 1. And then it grows closer and closer and closer to 0, but never actually gets there. So it's less than or equal to 1, but bigger than 0, because it can never actually hit a mass of 0, theoretically. Maybe after like 15 years of staring at the isotope, you'd be like, it's gone! I'm going to go home and spend time with my family now.
Oh, you have radiation poisoning.
So this is the same principle as like stepping like halfway towards the wall.
Yeah, Zeno's paradox, pretty much, yeah. Crazy stuff. Did I tell you guys about Achilles and the tortoise? That paradox? No. No? Maybe I'll tell you later. C, write the exponential decay model that relates the mass of radium-225 remaining in time to 15-day intervals. Okay? So, let me just be a little bit clearer here because the question sounds a little weird. Write the equation for the graph, is what they're trying to say. Okay, so when they say write the exponential decay model that relates the mass to the time, they're saying write the equation of that graph. Okay, so let's think about this. I've got mass, and that's going to equal some function of time. Okay, I know it'll be exponential, so I'll have like c to the power of t. And we're going to define t as 15-day intervals, just to keep things simple. So it's going to be a little bit different than that general half-life formula I showed you in the beginning. It'll be a little simpler, but still accurate. Okay? So let's think about this. The first 15-day interval, its mass would be calculated in the following way. We would start with 1 gram of material, and then after a 15-day interval, we would half it. Make sense? Giving us 0.5. Okay? The second, let me just move this up here a little bit. I'm running out of space. Okay, so the first day we start with 1, we half it, and we get 0.5. The second 15-day interval, we would take what we had before, which I'm just going to write in this form, because hopefully you'll see the pattern in a moment, and we half it again. And remember, just this part is what we had last time, 0.5. And then we're just halving that again. Okay, giving us 0.25. The third 15-day interval, we take what we had before. Okay, remember all of this is just 0.25. And we half it again. Can you see a pattern emerging yet?
Yep.
Okay, that's 0.125 and so on. Okay, so from this can you derive the equation y equals c to the x? Maybe I'll write it like this, see if this helps. I can write this guy as 1 times 1 over 2 to the power of 1. I can write this guy as 1 times 1 over 2 to the power of 2. This guy as 1 times 1 over 2 to the power of 3.
So it's going to be 1.5. Or not 0.5.
So it'd be 0.5 or just half, right? So the real equation would be half to the power of x. Do I need the 1 in front?
No.
Not really, right? 1 times anything, it doesn't matter. But just remember that there should be the initial mass in front. So if we started with 2 grams, then we would need that 2 in front. Okay? But since it's just 1, it doesn't really matter because 1 times anything is whatever. So here's our equation. Half to the power of x. Sorry, not x, t. It should be t. Because we're doing time intervals. There we go. D, estimate how many days it would take for radium-225 to decay to a 30th of its original mass. Okay, so what's a 30th of 1? Well, that's just a 1 over 30. So we want to know, in this equation, m equals 1 over 2 to the power of t. What value could I put in for t to make m equal 1 over 30? Okay, just do some test values. Try putting in different values of t until you get something close to 1 over 30. 5? 5 is pretty close?
Isn't this for a logarithmic?
Yeah. You can actually solve this equation using logarithms, which I would show you now, but completely lose the awesomeness of my lesson.
Look at our logarithm.
Can't you show us?
But maybe just think about this for a moment.
Negative log.
Right? How would you solve that? How would you solve for t? Because you're guessing. I'm telling you to guess. But how would you solve that?
2 times 2
Ooh.
times 2. So what you get the 30.
I just did 0.5.
How do you solve for variables that are in exponents? Ah! Yeah. That's what the next chapter is about.
Well,
Fun, right?
You'd use negative log to
Yeah, probably just a bunch of crazy stuff. So 5 days, you said?
Pretty close.
Gives you a really close value to 1 over 30? Good.
It's actually just a little bit less.
Just a little bit less? But, okay.